Okay, so welcome back. Right now we're going to start talking about electrolysis, especially as it relates to calculating for mass. So some things we need to understand is typically when we've set up galvanic cells, we've set them up with a cell potential that is positive, which means that typically the reaction is running from reactants to products, and so bracket that off. So reactants are going to products, which means that essentially the electrons are following that path of pushing through the system. Electrolysis is going to be forcing a current through a cell to produce a chemical change for which the cell potential would have been negative. So in other words, the non-spontaneous direction. So we're going to take electrons in the opposite direction. Alright, so electrolysis can be viewed through stoichiometry because electrolysis is often used to turn positive metal ions into the elemental metal. Basically what's happening is, normally we measure the push of electrons through the system through the potential provided. So what's going to happen is that potential, right, relates to a push in a particular direction. What's going to happen is we're going to use energy or work from an outside source to push the electrons back in the opposite direction. Alright, and so if we can figure out how many electrons are flowing through a cell, we can figure out how many ions will be changed to atoms and then figure out a mass of the element that has been formed. So basically we're thinking about all these types of equivalency statements, these bridges between information. And so what we're going to have is we're going to have information related to the work that's being done on the system. And so there's a few different numbers that we're going to need to have a handle on or have an understanding of as we read a problem. So in any electrolysis problem, things we want to identify, especially in electrolysis for mass problems, we want to identify the current. Current is typically measured in amps, and an amp is coulombs per second. So 1 amp is 1 coulomb per second. 2 amps would be 2 coulombs per second, and you can see the trend that's occurring from there, I hope. The only thing that we need to understand is the relationship between coulombs, which we would be getting through current, and then moles of electrons. And that comes through the Faraday constant. Remember that a mole of electrons has 96,485 coulombs. So for every mole of electrons, 96,485 coulombs. So I imagine that you can see now that it's probably going to take a good number of seconds to transfer a good number, to transfer the 96,485 coulombs required to transfer a mole of electrons. So those are really the two key pieces of information. So to remind us, current information and then understanding of the Faraday constant are the two things that we should be able to know off the top, right? Just as soon as we see electrolysis, Faraday constant we should have memorized, and then we should be reading the problem to identify the current information. With that being said, there's 4 steps that we're going to follow to set up our factor label that's going to solve for mass of the element that'll be formed. Alright. Time times current is going to get us to coulombs. Coulombs, as it relates to the Faraday constant, gets us to moles of electrons. Moles of electrons can be related to the electrons needed to be transferred to make the element. And then the moles of the element times the atomic mass gets us to the mass of the element formed. So let's go ahead and take a look at this example problem and see what we can work out here. So one of the nice things about electrolysis problems is that you don't need the reduction table. It's not gonna play a role in terms of what we're gonna do. So we have this question: what mass of zinc will result from passing 4 amps through a solution of zinc ions for 1 hour? Here we've identified our current, and the other piece of information that would be helpful to know is the length of time that this is going to be occurring, and we have 1 hour. So this now gives us the opportunity to start setting up our factor label. So we've got 1 hour And at this point, we've got options. We can go directly from hours to seconds, or we can go from hours to minutes to seconds. Because I imagine that you all could go from hours to minutes and minutes to seconds. I'll do this as a single step. So for every 1 hour, there are 3,600 seconds. This now gives us the opportunity, right? Hours are going to cancel out. Seconds are what's left behind. And seconds and coulombs have a relationship. Because it is a 4 amp current, for every 1 second, 4 coulombs are going to be transferred. So this gives now the cancellation of seconds and leaves us in coulombs. You may recall that I had mentioned that we need to have that Faraday constant memorized, because that's going to give us the bridge between coulombs and moles of electrons. It's 96,485 coulombs for every 1 mole of electrons. So now coulombs are canceled and we're left with moles of electrons. And so now we need to consider, alright, how many moles of electrons need to be transferred in order to get 1 mole of zinc solid. I could even put the solid there, though I'm not really all that worried about that. And in this case, we should recognize, given the charge, there's going to be 2 electrons, or 2 moles of electrons, to get us 1 mole of zinc solid. So moles of electrons, done there. And just to make it clear, this term is not mole minus, it's moles of electrons. It shows up a little bit better right here. But with that being said, now I've got that final step where I can get from moles of zinc solid to the atomic mass of zinc, 6538 grams, 65.38 grams of zinc solid. And so we're in a pretty good position to solve it out. So multiply across the top and divide by what's multiplied across the bottom. So just to remind you, it sometimes can be helpful to think about the bottom being in parentheses, and you may have noticed that the number that should be there for moles of zinc is obviously 1, because we're talking about molar mass. So across the top I've got 1 times 3,600 times 4 times 1 times 1 times 65.38. And so on the top I've got 941, 472. And for my bottom, I've got 1 times 96,485 times 2 times 1, so 192,970, which equals looks to be about, and with 1 hour, and there's not a whole lot of sig figs there, right? So I'm getting a calculator report on the order of 4.88 grams. Given that this appears to be 1 sig fig, might have to reduce that to 5 grams, but in either case, that's of zinc solid. Normally maybe they'd report this as 1.00 hours. They'd give us maybe some opportunity to get a number of sig figs determined for our answer. But that's electrolysis for mass, so I hope this helps, and good luck putting it to use for yourselves.